Hello students, this is the third part of my four-part lecture series on electrostatics, and in this video I'll be discussing the concept of electric field and some related problems concerning electric fields. What is electric field? Let's first look at the conceptual definition of electric field. So imagine that there is a positive center charge or big Q, and there is a small test charge which is also positive but small q sub 0. Okay, we know that there is an electric field around this big Q, the center charge big Q, because this smaller test charge experiences an electrostatic force, okay, at that particular point P. And if you're going to divide the amount of electrostatic force that that charge experiences, okay, divided by its charge, then we are defining conceptually electric field. We can liken it to the case of gravitational field of the Earth. So imagine that this is the Earth, and the region around the Earth is, of course, as we know it, it is called gravitational field of the Earth. We know that there is a gravitational field around the Earth because when there is a small mass m at that point, this small mass m experiences some kind of a force known as gravitational force. And if you're going to get the amount of force experienced by this small charge m divided by that value of small m, then we are defining what we call as acceleration due to gravity of the Earth. But this is, in this context, small g here is known as the gravitational field strength of the Earth. All right, so there is a parallelism between gravitational field strength and electric field, also known as electric field strength. Another way of defining electric field is by using what they call the operational definition. Okay, if the electric force on a positive test charge Q naught at a given point is represented by F sub E, or electrostatic force Fe, then the electric field E at that point is defined by this equation. E is equal to the limit of Fe divided by Q naught. Okay, as Q naught approaches 0. All right, what does this mean? This means that in this formula, Q naught is chosen to be as small as possible. Okay, how small? Very small, to the point that we are looking at a situation where Q naught approaches 0 but not equal to 0. All right, so that is the concept of electric field. All right, uh, the assumed Q naught, small Q naught, is too small as compared to the center charge big Q in this illustration. Okay, the reason for assuming that the small test charge is extremely small, so that its own electric field will not in any way affect the electric field of the center charge. Q naught, the small Q naught, may have its own electric field, but it may be considered very small or negligible. All right, so what is the SI unit of electric field? It is Newton per coulomb. All right, there is no single particular unit. It is just the unit of the force divided by the unit of the charge, Newton per coulomb. All right, so let me check your conceptual understanding about electric field. So in the equation, E is equal to F over Q naught. What happens to the electric field E if Q naught is doubled? Okay, here are the choices. The electric field, letter E, also doubles. Letter B, the electric field is halved. Or letter C, the electric field remains unchanged. So, how do we answer this question? Okay, this is the formula that we are focusing on, F over Q, or Q naught. So, if you double the denominator, which is Q naught, okay, it appears that doubling Q naught, okay, will make the electric field reduced by half, isn't it? Because they are, at the first glance, electric field seems to be inversely proportional to Q naught. So if you double Q naught, the denominator in the equation, its effect on the electric field E is for the electric field A to be reduced by half. But, okay, here is where the but comes in. All right. If you recall, in our part 2 of my lecture tutorial on uh, electrostatic force, okay, I have introduced, okay, the formula for finding the electrostatic force F, which is equal to K times the product of the absolute values of the two charges Q and Q naught divided by the square of the distance that separates the two charges. But in here, the formula for electric field is equal to F divided by the magnitude of the Q naught. So if you notice, okay, the, the value of F will be divided by the value of Q naught. So there is Q naught appearing in the numerator as well as in the denominator, which obviously can be cancelled out. Hence, we will come up simply with this uh, formula for finding the electric field in terms of the center charge Q. Okay, the Q here without the subscript actually can also be represented by a big Q. Okay, big Q or Q without the subscript is known as the center charge, divided by, of course, R squared. So, using this concept for electric field, all right, our answer should not be letter B. The electric field will not be halved when Q naught is doubled. In fact, okay, Q naught has nothing to do with the electric field. Electric field does not depend on the test charge Q naught. All right, so therefore, the best answer for this check your understanding question should indeed be letter C. Before we move on to our computational problem solving, there is something that I would like to emphasize about the formula for electric field in terms of the center charge Q. All right. So, according to this formula, even if the test charge Q naught has nothing to do with the electric field E, okay, in the first place, it is not the Q naught that owns the electric field. All right, it is the center charge. So the center charge is the variable that may affect the electric field. All right, and as you can see in the formula, the greater the amount of the center charge Q, okay, the greater is the electric field, or the electric field around that center charge Q. Okay, and any point around that center charge defined by the distance r. Okay, it says here for constant Q, K is constant, as we know that. So the greater the value of r, or in other words, if a point is farther, okay, if a point where we are going to evaluate the electric field is farther from the center charge, it follows that the amount of the electric field at that point should be smaller, okay, because electric field is inversely proportional to the square of the distance from that point to the center charge. So, in some of our problem analysis later, we will be referring always to this uh, formula for electric field. Okay. Before we discuss quantitative problem solving, let's have more concepts related to electric fields. Now we'll talk about electric field lines. Okay, these are lines of force provided that provides a map of the electric field in the space surrounding electric charges. So for example, here we have a center charge positive Q, okay, and we can imagine that at any given point, okay, distance r away from the center charge, okay, we can imagine lines of force, right? The lines of force, and these lines of force, oh, of course, the number of lines of force depends on how large uh, the charge, the amount of charge of the center charge. So the greater the charge, the more lines of force that we can imagine. All right. And the direction of the electric field lines also depends on whether the center charge is positive or negative. Okay. So what is the direction, or what are the directions of the lines of force? When the center charge is positive, we say that the electric field is directed away from, right? Away from the center charge. So at any given point, for example, at this point, it is upward. Down here, the electric field is, of course, downward. At this point, to the right of the center charge, we say the electric field is to the right. Or at this point, to the left of the center charge, we say the electric field is to the left. Okay? But in case if the center charge is negative, we say that at any given point around this negative center charge, the direction of the electric field is towards, okay, the negative center charge. All right, we said this earlier that the number of lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. Now, what about if there are two center charges? Okay, and supposing they are opposite charges. Okay, how do we describe the net electric field around these two charges? And what if the two charges are of the same sign? So let's look at the case first for two center charges that are opposite in signs, a positive charge and a negative center charge. So this is how we visualize, okay, the electric fields around each given charge and, okay, on a space between them here. All right, so we still followed our conventional sign or direction for determining the electric field direction, okay, in terms of what the center charge is. For a positive center charge, we say it is outward or away from the positive center charge. But for the negative center charge, uh, the electric field lines are towards. So we can imagine that these electric fields for both, okay, there is a certain space around them where, okay, the two electric fields will reinforce or will add up. Okay, the point that is exactly halfway between positive Q and negative Q, somewhere here, we say that the electric field, the net electric field, is greatest. All right, that is where the electric field, net electric field, is maximum. But as we go farther from each of these center charges, then there is also a decrease in the value of the net electric field. Supposing at point 1, all right, we can imagine that the electric field due to the first charge, we call it electric field number 1, okay, we can imagine that at that point, the instantaneous electric field due to Q, positive Q, is directed tangent to that curve, okay. The electric field lines is now a curved line, and at that point, tangent, we can imagine the electric field due to positive Q. And at point 2, for example, we can also imagine a line tangent to that point, okay, if you want to define the electric field due to Q2, right? So anywhere at this point, we can actually describe, okay, the electric field due to Q1 or due to Q2, or even the net force or electric field, okay. But what if the two center charges are of the same signs? Say, for example, they are both negative or they are both positive. So this is what's going to happen. There is a portion between them there where the net electric field becomes zero. It's like the two electric fields due to Q1 and due to Q2, which are both positive, will seem to cancel out. All right? As you can see, the electric field lines seem to oppose each other, and a point where there is a total cancellation of the electric fields, resulting to a zero net electric field. So there is a difference between these two cases in terms of determining the net electric fields, okay, brought about by two charges or center charges. Another important concept regarding electric fields, supposing we are talking about two parallel uh, metal plates that are charged. One is positively charged and the other is negatively charged. So we say that the electric fields, okay, between these two parallel charged plates is such that when we visualize the electric field lines, we can imagine that uh, they always begin from the positive, all right, or yes, from the positive plate to the negative plate. And there is no such thing as an electric field that stops, okay, in the in the middle of the two charge plates. Okay, so right here at the very center, we can imagine that the net electric field is in fact stable or constant, all right, as shown by these straight lines, electric field lines. But as you go closer to the opening, all right, notice that there is some kind of uh, what do you call this? There is a curving. The tendency for the electric field lines is to curve outward. Okay, that simply means that it's somehow decreasing in amount or value, right? So at any point here between this positive charge plate and the negative charge plate, okay, the amount of electric field is in fact constant or uniform. Okay, whether you are talking about a point closer to the negative plate or closer to the positive plate or at the very middle point, okay, the amount of electric field is the same or constant. All right, so this particular illustration shows us that uh, whenever we have three possible sources of the electric fields, right, such as in the first illustration, supposing we have these two metal plates, fixed metal plates, one is positively charged and the other is negatively charged, and there is a negatively charged rod, all right, here. And we imagine a point here, okay, where there is a small test charge whose amount of charge is given. For example, a charge of positive 18 times 10 to the negative 8 coulomb. Naturally, this test charge Q naught will experience a net force, okay? A net force that is the result of the individual electrostatic force that is exerted by each uh, source of the force. Okay, this positive charged ball, okay, will influence the test charge. Okay, it will kind of repel the test charge because the test charge is always assumed to be positive. Therefore, it experiences a force of repulsion from this positive metal ball. And at the same time, the negative metal ball will also influence, okay, the test charge. Since this is negative, the positive test charge will sort of be attracted into this negative charge ball. And lastly, the negative charge rod will also has it or will also exert, okay, an attractive force on the test charge. And if you're going to add all the three forces, okay, you will be able to describe the net force going into that direction as indicated by the blue arrow. And if you're going to divide that amount of force, net force, by the amount of Q naught or the charge of the test charge, you will be defining the electric field at that point. Okay? And for a test charge that's positive, okay, we describe the direction of the electric field to have the same direction as the net force. That is the meaning of this letter A illustration. But what if the test charge is negative? Okay, negative 24 raised to the negative 8 coulomb. Okay, for the same surrounding center charges. Okay, the test charge will experience a net force that is directed as shown by the blue arrow. Okay, exactly the opposite of the first illustration. Okay, and the net electric field, okay, here will now be opposite. All right, opposite to the direction of the force or net force. So that's the difference between these two cases. Okay? We therefore summarize that if the test charge is negative, all right, the direction of the electric field at that particular point is in the same direction as the net force that the test charge experiences. While if the test charge is negative, then the electric field defined at that point is opposite in direction to the net force. All right, so for our quantitative problem solving, uh, it's now our example 2, okay, which talks about an electric field leads to a force, okay? So the charges on the two metal spheres and the ebonite rod create an electric field at the spot indicated, okay? The situation is similar to what we have just discussed earlier. The field has a magnitude of 2.0 Newton per Coulomb. Question is determine the net force on the test charge Q naught in case A as well as in case B. So case A is such that the given test charge Q naught is positive, while in case B, uh, the test charge is negative and it's also has a greater value for its charge. So we shall look at the solution in the next slide. All right, so in this problem, we emphasize that the given electric field is the same for the two cases, okay, which suggests that it really doesn't matter what the test charge Q naught is, okay, since this so-called net electric field does not depend on the test charge Q naught, but in fact depends on the surrounding center charges. So for our first question, letter A, we are looking for the net force at that particular point for a positively charged test charge 18 times 10 to the negative 8 coulomb. So what we did here is just to multiply, okay, multiply the given electric field, which is 2.0 Newton per Coulomb, and multiply it by the magnitude of the test charge, okay, which is 18 raised to the negative 8 Coulomb. The unit Coulomb cancels out, and we will get this amount of the net force, 36 times 10 to the negative 8 Newton. Okay, so since we use the absolute value for the Q naught, we don't expect any specific sign for our net force. And for the direction, you simply refer to our diagram. Okay, our diagram suggests that the net force is directed as shown by the blue arrow. Now, how about for the letter B case, where the test charge is now changed, okay, to 24.0 times 10 to the negative 8 coulombs, all right, and multiplying by the same amount of the electric field, we get 48 times 10 to the negative 8 Newton as the net force in case letter B. All right, so the net force for the two cases, the net force is not the same because for a constant electric field, okay, the amount of net force that a test charge experiences also depends on the amount of the test charge. Okay, in letter B, the amount of the test charge is higher or greater than that in case A. So expect that they will not have the same amount of net force experience, okay, uh, at a point with the same electric field. It is also emphasized here that for cases where there are two possible sources of the electric field at a given point, like for example, there are center charges at point A and at point B. Supposing they are both positive center charges. Okay, so at point P, we define each electric field, okay, due to, for example, due to center charge A, we say that at point A, the direction of that field due to center charge is to the right, all right, because point P happens to be to the right of the center charge, all right. So that arrow, okay, the red arrow directed to the right represents the electric field due to center charge A, while the electric field at the same point P, okay, brought about by center charge B, okay, which is also positive, then uh, the electric field, okay, at point P due to charge B is also away, okay, away meaning it is downward. And if you're going to get the vector sum of these two electric fields, then we just draw an arrow, all right, like this, represented here by this diagonal arrow, which defines an angle theta with the uh, x-axis, or the theta here is below the x-axis, and the resultant electric field here, okay, can be determined mathematically if you're going to apply the Pythagorean formula. So we summarize that electric fields from different sources simply add as vectors. This is one very important concept in understanding electric fields, especially when we relate it to our next concept to be discussed in the last part of the lecture series. I'm referring to electric potential as well as electric potential energy. Right, so for now, this is how we consider net electric fields brought about by two center charges. We add the individual electric fields as vectors in determining the net or total electric field. Here's now example number 3. The electric field of a point charge. The isolated point charge of Q, which is equal to positive 15 microcoulomb, is in a vacuum. Okay, the test charge is 0.20 meters to the right and has a charge Q naught equals positive 0.80 microcoulomb. Determine the electric field at point P. So in our illustration, letter A, we have here the center charge Q with no subscript. It's positive. And to the right, a distance R. At point P, we have the test charge Q naught. All right? And this test charge Q naught experiences a force F. Since the center charge is positive, then the force that the test charge experiences must be directed to the right. And in illustration letter B, we also have the representation of the electric field, okay, at that same point P. This electric field, take note, is the electric field owned by the center charge, small q without the subscript. So that's our illustration. And we are asked to find the electric field at that point, point P. So our first solution or formula is to first determine the amount of force F, right? The amount of force F that the test charge experiences simply using Coulomb's law equation. We just substitute the given and we get the amount of force equals 2.7 Newton. Take note that in substituting in the formula, you have to convert, all right? You have to convert the given charges, okay, from microcoulomb, convert them first to microcoulomb, okay? All the quantities have to be expressed in SI unit, okay, before doing your multiplication and your division. So we get 2.7 Newton. That is the amount of force F. And then, knowing the amount of force, we can now use the simple conceptual meaning of electric field, F over Q naught, where 2.7 Newton is divided by the amount of test charge, which is 0.80 to the negative 6 coulomb. Okay, so we will get this amount of electric field, 3.4 times 10 to the 6 Newton per coulomb. All right, that is the long method, 2 steps. But actually, we can also use a shorter way. And that shorter way is using the formula E is equal to K times Q over R squared, where Q here is the center charge. Okay. Notice in the formula, we don't need the test charge Q naught. Okay. So substituting the value for K as well as the value for the center charge already converted to coulomb and dividing by the same value of R. Okay. And doing our math, we will get the value for the electric field, 3.4 raised to the 6th power Newton per coulomb, which is exactly the same as what we got earlier. Okay, so I have shown you two ways of determining the amount of electric field. If the force can be calculated, okay, you can do it, then just calculate for the electric field using that amount of force. But if you're in a hurry and you just want the electric field, okay, you can use this shortcut formula. So that's it. All right, so the electric field of a discrete charge distribution at an arbitrary point is just the vector sum of the electric fields of the individual point charges. Okay, what do you mean by that? Supposing there are two or more center charges, okay, and we want to also determine the net electric field at a given point, a distance r, all right, from each center charge. So we just use the formula E is equal to K, and actually this symbol, Greek letter sigma, refers to the summation of all the product K of K times big Q divided by, all right, divided by the distance r squared. Okay, so it means that if there are two center charges, then each charge will have a certain value for r, okay, and we simply add them after having multiplied the value for, divided the value of q and r squared, since they have common, what do you call this, constant of k, we just use this notation. All right, that's exactly what our next example is trying to let us apply. So example number 4, 2-point charges are lying on the y-axis as in the figure. Okay, the figure will be in the next slide. Q1 is equal to negative 4 microcoulomb and Q2 is positive 4 microcoulomb. They are equidistant from the point P, which lies on the x-axis. What is the net electric field at point P? Whereas show our vector diagram. Alright, so this is our illustration first, or what we call vector diagram. The forces acting on Q sub 3. Right? Back to the situation, the diagram of the situation. It says that the first charge, which is negative Q1, is located somewhere here. And then down below, a distance of 10 centimeters below, we have positive Q2. All right, these are considered the center charges. And at a point P, which is 13 meters away from each charge, all right, 13 meters or centimeters away from positive Q2 and 13 centimeters also away from negative Q1. All right, so what we are going to include in our vector diagram is the forces acting on Q3. All right, Q3 is to be what do you call this, to be assumed located at point P, right? At point P, that is where Q3 is supposed to be located, all right? In other words, Q3 will experience uh, forces due to center charge negative Q1 and due to charge Q2. But what we are going to label in our vector diagram, okay, are the electric fields. The electric fields at point P due to negative Q1 and due to positive Q2. So here is our vector diagram. First, uh, just look at first the solid arrow. Right? At point P, we label the electric field due to Q1. Right? Why is the arrow directed towards Q1 or negative Q1? The reason is Q1 is negative, and therefore we pointed out earlier that if the center charge is negative, all right, the electric field at any given point around it is into the charge, meaning towards negative Q1. Hence, our arrow representing the electric field due to Q1 at point P is directed towards negative Q1. Okay, and we can define that angle alpha, all right, uh, with respect to the horizontal or to the negative x-axis. Then what about the electric field at the same point P, okay, due to positive charge Q2? All right, since positive charge Q2 is positive, therefore, at that given point P, we can say that the electric field is away from, all right, away from the center charge Q2, which exactly is what is represented by the red solid arrow, E sub 2. Right. So far, that is what we can say about the two electric fields, okay, at point P, okay, and that is our vector diagram. Now, what are these broken arrows? What do they represent? Okay, so just like in our previous video tutorial on forces, okay, that was part 2 of our video tutorial. Okay, we emphasize there a method known as the component method, okay, of determining the net force, especially if the two forces involved are not along the same straight line path. All right, like in this case, the electric field E1 and electric field E2 are not along the same straight path. They are neither in the same direction nor in opposite directions, but they make an angle alpha with respect to the horizontal. So the best way to determine their sum or vector sum is using the method which we call the component method, meaning we are going to resolve them one by one, getting the vertical component and the x component. Okay, we start with ease of 1. Okay, we first determine exactly what the value of E1 using our formula KQ1 over R squared, right? So substituting the value for K and the value for Q1, disregarding the sign, all right? This is just the absolute value. And how far is Q1 from point P? It says 13 centimeters, and that's 0.13 meters. Square it. So we will get this value for E1, 2.1 times 10 to the 6 Newton per coulomb. The direction is as indicated by the blue arrow in our vector diagram. And for E sub 2, or electric field due to Q2, same formula actually, okay? The same value for absolute value for the charge and the same distance r. So we expect the same answer magnitude-wise. All right, 2.1 times 10 to the 6 Newton per coulomb. But they differ in direction because E sub 2 is directed according to the red arrow in our vector diagram. Now, this is now how we are going to determine each of their horizontal and vertical components. All right. We say that each x component for both E1 and E2 will have the same magnitude. The fact they are equal in magnitude, therefore it follows that their x component will also have the same magnitude, but exactly in the opposite direction. And that's how we are able to say that the summation of EX, all right, the summation of EX will just be equal to 0, right? And using the definition of sine of that angle alpha here, okay, we can actually determine what the value of alpha is based on our original, what do you call this, illustration here. Okay, you will notice that this angle alpha is the angle that is formed by that distance, which appears to be the hypotenuse of the right triangle that we can imagine here. All right. So alpha is defined as the angle formed by 13 centimeters, okay, and the opposite side, which is 5 centimeters. Hence, if we want to determine that angle alpha, we can actually use the relationship of the hypotenuse and the opposite side, which is exactly the meaning of sine of the angle alpha. All right, and in determining the value of alpha, we just use the formula for inverse sine. Okay, we just get the ratio of 5 centimeters over 13 centimeters. All right, and using your cycle, okay, you can actually determine the value of alpha, which is equal to 23 degrees. All right, so that is the value of alpha or angle alpha. Now, to determine the y component of E1, okay, which again, E1 and E2, all right, E1y, we call them E1y and E2y, they are both directed upward, okay, or towards the positive y-axis, okay, if their x components have the same magnitude, okay, but opposite in directions, that's why you're able to cancel them. For the vertical components, E1y and E2y, we cannot cancel them because although they are equal in magnitude, but they are in the same direction, all right? So each one will be determined using sine of the angle, which is 23 degrees, multiplied by the computed value for E1 or E2. All right? So that is 2.1, right, times 10 to the 6 Newton per coulomb. Using your cycle again, we will get the value of the vertical component of each E1y as well as E2y. They are just equal to 8.2 times 10 to the 5th power Newton per coulomb. And since we are looking for the net or total, all right, total electric fields, we already canceled the two x components, e sub 1x and e sub 2x. We are left with the two vertical components, e sub 1y and e sub 2y, adding them together vectorially. Then we will get 8.2 times 10 to the 5th newtons per coulomb, just multiplied by 2. And this is what we will get as our answer. E net equals 16 times 10 to the 5th Newton per coulomb. And the direction, of course, as shown in our vector diagram, they are directed towards the positive y-axis. So that ends our computation and also our discussion for today's tutorial. Thank you very much, and see you in our last part of our series of lecture tutorials. Thank you very much.